We'll talk on this lecture on unsteady state mixed flow reactor and the plug flow reactor. As we know, at starter of PFR and MFR, we need time to reach steady state. So this time will depend on what we have of reactor type. So in a plug flow reactor, as we assume that plugs will move till the exit of reactor. So we know that tau for a plug flow reactor is equal to L over U, and for the first tau exit of the reactor, and that we can put as time needed to reach steady state. So for PFR we need 1 tau to reach steady state. In CSTR we have different things, as we know that for these particles come here and move, these particles come here and exit, these particles come here and exit, and we have also some particles still in the dead zone. So we need to compute steady state time practically. So to compute unsteady state for MFR, we will have CSTR like this. Here will be V naught, CA naught, FA naught, and XA naught, and at the out we will have FA, CA, XA, V. XA not always is 0 unless he told us that we have some product in the reactor. So by making mole balance here, N equal to out plus reaction plus accumulation. So V naught CA naught will equal to V CA plus minus RA multiplied volume plus volume dCA over dt. Here we are talking about time need to reach a steady state. So we know that everything with time is equal to 0 at a steady state, but here we have to fill this until reach steady state. So we need some times, and we want to derive or try to compute this time. And this is equation 1. So V naught, and assume reaction is first order. So minus RA will equal to K CA. So V naught CA naught will equal to V CA plus K CA V plus V dCA over dt. And let this equation 2. Now we'll divide on V. Since we know that V naught will equal to V for liquid phase, so when we divide over V, we will have CA naught equal to CA plus K CA, and let's when we divided V over V naught over V, this will be tau plus dCA over dt, and this is equation 3. Now we will have dCA over dt. On the arrangement of this equation, we will have 1 plus tau k over tau. Here also we will have tau, and this will be Ca minus Ca naught over tau equal to 0. And let this equation here, we said that is 1, this 2, this 3, and this 4, and this 5. So this equation correlates change of concentration with time to reach steady state. So we know that only boundary condition at T equals 0, Ca must equal 0. Here as we have T equals 0, we say that Ca equals Ca naught. But here we're talking about the exit concentration for this figure, this Ca. At time equals 0, this Ca, there is no concentration here, so it will be 0. And this is the only boundary condition we will use to solve this equation. So the solution of this equation will give Ca equals Ca naught over 1 plus tau 1 minus exponential minus 1 plus k tau over tau multiplied by time, and this is equation 6. So you have to know how we reach this equation. You can go back to what you study on math in stage 2 or in stage 3. Now let us define something known as Ts, which is the time necessary to reach 99% of steady state concentration, which will be CAS. So CAS will be equal Ca naught over 1 plus k tau, and this is equation 7. Now sub equation 7 and equation 6, we will get Ca equal to CAS 1 minus exponential minus 1 plus k tau over tau Ts, and this is equation 8. This is T, not Ts. Now for reach to 0.99 CAS equals CAS 1 minus exponential minus 1 plus k tau over tau Ts, and you can CAS with CAS. So solving for Ts will give 4.6 tau over 1 plus k tau, and let this is equation 9. So we can see that time to reach a steady state is 4.6 tau over 1 plus k tau. Now, if tau k is less than 1, which means, let us say, for slow reactions, this means tau k is less than 1, or take tau k equal to 0 comparing with 1, so Ts will be equal 4.6 tau, and we know that's 4.6 V over V naught. So we need almost 5 taus to reach steady state for first order reaction. For fast reactions, this means that tau k larger than 1, so Ts will be 4.6 tau over k tau, and that will give 4.6 over k. We know that k is almost less than or always small, so for fast reaction I expect that Ts equal 4.6 over k, which is its number is larger than for the first case we take in this equation. Now I think if you go back to equation 6 and we try to represent it, this will give Ca over Ca naught with time, and this will just like this, and this for tau k equal to 1. You can change tau k and see how this figure changes. Now, from all that, we have to reach two cases. First one, we have to fill up an inert and starting our reactions. Then after reach steady state, we add our material. To fill up with Ca naught only and start flow to ensure that Ca exit will equal to Ca naught till we reach steady state, and then we start our reaction. This is all thing about time to reach steady state. What I want you to do is do these steps, but take minus Ra equal to Kca square and see how that will change, and let's that our or your homework for the next week. I expect your solution on the next week for this type of reaction. I think this is enough for this lecture. On the next lecture I'll talking to you about recycle reactor and how to derive or mole balance for reactions if we have some recycles go back to mix with the input reactor.